Hello and welcome back to Physics for the 21st Century. Again, my name is Greg Perugini and I'm your guide through this course. And this is the fourth topic, vector algebra, and a little bit of a review on trig and geometry, what you need to, and you should already know in terms of how to manipulate vectors. So let us sort of begin through this. So if you remember, as we talked about before, vector quantities are physical quantities that have both a numerical and a directional property, a magnitude and a direction. So what we're going to do in this particular chapter, this particular topic rather, is addition and subtraction of vectors. So how do we go about that? Let us take a look at this. Just a brief outline of where we're coming from. You should all know what I'm doing here in terms of the Cartesian coordinates. I'm going to just talk about x and y for now, and we could talk about z coming in and out of the board as well. But from the origin, if I have a point here, let's say about there, we can describe this point by how far and how much it is in the x direction and how much it is in the y direction. If we think of this angle here, this is the opposite side of that angle, and this is the adjacent side of that angle. And so if we say that this length here is 2 and this length here is 3, and it could be in any units. Let's use meters per second as a vector. This point here, you're probably familiar with seeing it in this notation, and you should already know how to get this hypotenuse and how to work with the adjacent side and the opposite side. Using these trig identities, the cosine of an angle is equal to the adjacent side over the hypotenuse. The sine of the angle is equal to the opposite side over the hypotenuse. Tangent of the angle is equal to opposite over adjacent. If I have the opposite and adjacent side, I can get the angle by doing tan inverse of opposite over adjacent. That will give me my angle. Now, I could also get what this hypotenuse is using Pythagorean's theorem. C squared equal a squared plus b squared. Okay? Or in this example, the hypotenuse of this triangle is equal to the adjacent side squared plus the opposite side squared, and you take the square root. So that's a little bit of a review as to just the basics, and you might want to get this down in your head and get this on a piece of paper. So at this point, let's take a look at where we can go from here with an example. So if I have, well, let's just take that one that we were just looking at. This is in the 3 here, 2 in the adjacent side. So we have this as being that coordinate there, this being the origin. in terms of x and y on the Cartesian coordinates. So, looking at that, how would I describe this fully? Well, if I want to get the magnitude and direction, and that's often called the polar coordinates, where you get the magnitude and the angle, to describe this vector completely, I need the magnitude and the direction, the units and the angle. Say this angle. It's common to take it from the positive x-axis and go counterclockwise. That is the standard, I should say. So what we have here, if we use Pythagorean's theorem, I should be able to find out what this hypotenuse is by just taking the square root of 2 squared plus 3 squared. And let me get out my trusty calculator and do that. And what I get is 3.6. Now, of course, I should add my units here. Let's say this was 2 meters per second as the vector, and this is 3 meters per second as a vector. Then what I just came up with is 3.6 meters per second. Now, remember what we did previously. How would I get what this angle is? Tan inverse of the opposite side, 3, over the adjacent side, 2, will give me my angle. Let me get my calculator out here, and I'll do that. And we come up with 56 degrees. So, if I want to describe this particular vector, let's call this vector A. I can say it in English and just say it is 3.6 meters per second, 56 degrees north of the positive x-axis. I could write it in polar coordinates. 3.6 meters per second, 56 degrees. And that would fully describe it as well. So, the book has another example, and let's do that other example. How would I describe this vector? Now, in the x direction, it is a negative 3.5. And in the y direction, it is a negative 2.5. But how would I calculate its magnitude and direction, its polar coordinates? This is in the y. And again, it's negative 2.5 in the y. Its strength is 2.5. Its strength in the x direction is a 3.5 negative. This is the x side. I could get the angle pretty clearly, right? I can look at this and say, how do I get this angle? As we did it before, tan inverse, right? Opposite over adjacent. Tan inverse of 2.5 We could do the absolute value here because we're just looking for this degree over 3.5. Okay? Or, well, I'll let you calculate that with me here. So let me calculate that. Tan inverse of 2.5 divided by 3.5. That equals 35.5 degrees. Now, given that, this being 35.5 degrees, polar, we take it from the positive x-axis. How many degrees is that? Well, it's 180 plus 35.5. 215.5 degrees. How large is it? What is this number here? What is its magnitude? Again, to describe this vector fully, we need the magnitude and direction. So, we go back to old Pythagorean's theorem, right? So, to get what that is, the magnitude, we take the square root of 3.5 squared plus 2.5 squared. Okay? And what does that yield? Well, we'll show that in a slide coming up. You should be getting 4.3. If this is meters, then of course your answer is in meters. So to describe this fully, in polar coordinates, it's 4.3 meters, 215.5 degrees. Okay? So now, in review of what we've just covered, take a look at this. You have the Cartesian system, again as I wrote, y, x-axis, and I can describe 3 points as strengths describing them as their strengths in the x and in the y direction. Polar, as I said, would be, in this case they use the notation of r, angle. Forgive me, my writing isn't too good on the screen. From the origin point in the x and the y direction. In most cases in physics, we want to deal with not the components, but we want to find the magnitude and the direction to completely describe the vector. In order to do that, if I have the vector itself, I can break it into its components, its x and y components, using trig, and I can use Pythagorean's theorem if I know the components, like we did in an example, but don't know the magnitude of the vector. And, as we did, using tan inverse to get the angle. So, well, before we go into a summary, let's do another example here. We're going to take a couple of vectors here. A guy is taking a hike, and this actually is an example in many textbooks. But he walks a certain amount of distance directly. Let's say he walks 25 kilometers directly southeast, which would be, if I drew that correctly, hold it. Let's draw that directly southeast. This would be 45 degrees. .25 kilometers. That's the distance. Then walking 40 degrees, or excuse me, 40 kilometers in a direction of 60 degrees north of east. Like so. This means 60 degrees. Walking 40 kilometers. After that, from point A at the origin, point B, then point C, how far is she from point C? From C to A, I should say. That's what we're trying to find out. The way we can find that out is we can do vector addition by breaking each vector into its constituent components. It may be helpful to do this via a little matrix here. In the X and the Y direction, from A to B, okay, that's one vector. Then we have another vector from B to C. Now I could actually label those vectors as vector 1 and vector 2. Vector 1 and vector 2. Okay? A little bit hard to see on the board. So let me redraw that again. Vector 1 is from A to B, and vector 2 is from B to C. So remember, we know that cosine of an angle is equal to the adjacent side over the hypotenuse. Just like we know that sine of an angle is equal to opposite over the hypotenuse. Well, if that's the case, if I am looking from A to B for this particular vector with this particular right triangle, and I say this angle is 45 degrees, the opposite side, right, is the y direction. It is negative. Okay? So in the y direction, we can rewrite this as saying hypotenuse times sine of angle. That is what's going to equal the opposite side. So what is this opposite side? This opposite side is 25, right? The hypotenuse times sine of, in this case, 45 degrees. It's going to be a negative. We're in this negative quadrant in the y direction. In the x, we can use the cosine equivalent to what we just did. And it's 25 positive in the x direction cosine of 45. Let's do the similar thing for this triangle right here. This angle being 60 degrees, we know that it's 40 kilometers positive x direction the adjacent side to this angle is in the x direction, adjacent to the angle, and the angle is 60. The other is positive y direction, and it is sine of 60. Those are the components in the x direction and the y direction for these two particular vectors. Vector A plus vector B will give us vector C. So we can do the vector addition here. What is the vector addition? Well, let me pick out another marker here. (25) times cosine of 45, which is 0.707, gives me 17.7 here. Okay. 25 times sine of 45, negative, it's going to give me negative 17.7. 40 times cosine of 60, cosine of 60 is equal to 0.5, so 40 times that is going to give me a 20 positive. And 40 times sine of 60, 86.6 sine of 60 times 40 gives me 34.6. Vector addition. If I say vector 1 here plus vector 2, if I draw a line back to the origin, must equal vector 3. If I add those two vectors together, vector 1 plus vector 2 is equal to, in this case, 17.7 plus 20 equals 37.7. 17.7 negative plus 34.6 is 16.9. Those are the components in the x direction and the y direction, and we could write this particular point as 37.7 and 16.9. Now, often you're asked, what is this magnitude and direction? If someone were to walk directly from point A to point B, they're going to need to know how far to walk and in what direction to walk. Okay, so they need both things, how far to walk and what direction to walk. So we don't know with this its magnitude and direction yet, but we can get that because we know, if I were to draw this even separately, that its y is 16.9 and its x is 37.7. Okay, how do I get that angle here? How do I get the hypotenuse? Just like we did before. The hypotenuse, let's call this here number 3. Vector 3 is equal to the square root of 37.7 squared plus 16.9 squared. Pythagorean theorem. That gives us 41.6, and since the unit's in kilometers, this distance is 41.6 kilometers. Okay? Again, I want to describe this completely, and through polar coordinates we can clearly see I need to give the direction as well, right? So what is the direction? Well, I can do tan inverse of opposite side here, 16.9, over adjacent side, 37.7, and that's going to give me my angle. That angle is 24.1 degrees. So we have everything necessary for a person from point A to know how to get to their final point. After they walked from A to B and then B to C, the final position, the vector from A to C, is going to be 41.6 kilometers, 24.1 degrees. Let me write that a little better for you right here. 41.6 kilometers, 24.1 degrees. So in summary, you have to know how to add and subtract vectors. You can use the polar or rectangular method to solve. You still need to know that opposite and adjacent side for getting the angle. You must completely describe a vector. Completely describing a vector means magnitude and direction. Stay consistent with your method and read the problems carefully. Check your work. Now, one of the things you might have noticed, if you remember all of your trig, is that I can calculate here my cosines and sines and stay consistent with sines and cosines. Let's just take this in the y direction and this in the x direction, and let's say this is 45 degrees and this is 30 meters per second. This particular vector A is the vector. Okay, so given that, if I have a vector, that's an easy one to describe, right? If we write our little matrix out, we can use cosine of 45, 30 times cosine of 45 in the x direction, 30 times sine of 45 in the y direction. We can stay consistent with cosine and sine, providing we always take it from the x, positive x, when we go around. If I say this angle here, 30 degrees, I can immediately describe vector B here. This is vector A, then this is vector B. Let's say this is 40 meters per second. As 40 times cosine of not 30 degrees, but starting from here and going around, 30 plus 90 is equal to 120 degrees. When we do this, you'll get the same answer as we got before, only this will put in the negative and positive signs for the correct quadrants. If I have a vector here, let's call this vector C. Okay, that's vector B, this is vector C. And this is the angle here, and we're going to say this is 20 degrees. I can immediately put cosine here. And if this is a vector of a magnitude of 50 meters per second, and immediately put the 50 there and 50 here and sine here, if I count directly from the positive x-axis and go all the way around, how many degrees is that? That's 200 degrees. Now, if you get out your calculator and do 50 times cosine of 200, you're going to get, 46.9 degrees negative, or 46.9 meters per second negative. The calculator, when it calculates the cosine of 200, will automatically put in the negative for the x direction, and it is in the negative x direction. Sine 50 meters per second times sine of 200 equals negative 17.1 meters per second. So doing it using a polar method, always starting from the x0 direction and going counterclockwise, getting the degrees, you will always have cosine in the x direction and sine in the y direction. You could also quite readily do this way. This is 30 degrees, right? In the x direction, negative 30 degrees, and for this particular angle, it's the opposite. So, cosine, opposite side, sine of 30, negative, is going to be equal to the cosine of 120. Okay? Check me out on that. So in summary, as I said again, read the problems carefully and check your work. Stay consistent with the method, whether you're using the opposite and adjacent method of a rectangular calculation or whether you're doing the polar coordinates as I've just described here. And know how to add and subtract vectors. You will be getting problems on how to add and subtract vectors. And good luck.